Hello, my name is Feng from University of Warwick. Here I'm going to present our paper on augmented password authenticated key exchange. This is joint work with Samiran, Liqun, Chen, and Paul van Oorschot. There will be three parts in this talk. First, I will review the field of password authenticated key exchange, in particular on balanced peg. And second, I will focus on augmented peg. This is related to balanced peg, but is a different problem. And third, I will present a new augmented peg protocol called OWL. What is password authenticated key exchange? In this setting, we have two parties. They have a shared password. This is a weak secret. As an example, the secret could be 3 digits, so that is only 10 bits. Based on the low entropy secret, the task is to establish a high entropy session key, for example, 128-bit. This problem had been thought of impossible for many years until 1992. So Bellowin and Merritt proposed the first solution called encrypted key exchange. Their idea is to use password as a symmetric key to encrypt Diffie-Hellman key exchange protocol. So in this case, W is the password. The assumption is that the public key is random. So when you use password to encrypt random data, that should be fine. However, it was pointed out 4 years later by Chen that this actually leaks information about the password. As an example, if the attacker intercepts a ciphertext and tries a password to decrypt this ciphertext, if the decryption gives a result of a value greater than P, then you know that the password is wrong, and attacker can test other passwords. The problems of EKE motivate a different design. So here we have another classic protocol called Simple Password Exponential Key Exchange, or SPIC, proposed by Jablin in 1996. The key idea in this protocol is to use a mapping function, that is F function. This function maps a password to a random generator. In the case of SPIC, the SPIC defines a set prime as modulus and defines a simple function for the mapping function. However, this definition of the mapping function has several issues. The first is that because of the use of a set prime, the exponentiation is expensive. And the second, there's no elliptic curve support. In 2008, together with Peter Ryan, we proposed a solution called Password Authenticated Key Exchange by Jargoning. In this case, Alice and Bob generate two pairs of random public keys, they exchange public keys, and they generate a new public key, they exchange it, and in the end, they compute a shared secret. So if you see the public key as a ball, it's like the two parties are performing a juggling game. The key idea here is to use zero-knowledge proof to prove that the received public key is well formed. In other words, the sender actually knows the private key. This protocol is flexible with many group settings, in particular DSA group and also elliptic curve. Today, this protocol has been used in many applications. So in this talk, we are going to modify this protocol to make it work in an augmented setting. So that leads to part 2, augmented peg. There are two types of peg schemes. So far, we have only covered balanced peg. In the case of balanced peg, Alice and Bob have a shared weak password, which are the same. In this setting, we don't normally consider the storage of the password. However, in some applications, we have to consider the storage of the password, and that is in the augmented peg setting. The idea is similar to Unix login. The user supplies a password, and a one-way transformation of this password is stored on the computer. However, the difference here is that the login is not done on the local computer, but over an insecure network. And this is done without a PKI. One classic solution to this problem is SRP6A, proposed by Wu in 2009. This is an improvement from an earlier protocol, SRP3, initially proposed by Wu in 1998. The original protocol has been revised several times to address certain attacks. In general, there are a few issues with SRP protocol. The first one is heuristic security. The protocol has been revised several times. Second, the protocol has the protocol mandates the use of a set prime as modulus. As a result, the exponentiation is expensive. And third, there's no elliptic curve support. In 2018, a new protocol called OPEC was proposed. And 2 years later, this protocol was selected by IETF as a new standard. The original paper provides formal secret proofs in the UC model. However, the specification was incomplete in the original paper. The two main building blocks in this protocol, the first is a F function. This is the same F function as used in SPIC in 1996. As a result, it also inherits the problems that we already know from the SPIC protocol. And the next one is the KE is a key exchange function. So after this protocol was selected as a standard by IETF, it was discovered that there's one such issue that is not covered in its secret proof. During the registration phase, the client compute subtext C, and this C use a key derived from a password. So in other words, if the password changes, then the value of C will change. During the login phase, for every login session, the server always sends the C back to the client. So if the user has updated the password, then the value of C will be different. So this leaks information about the fact that the user whether or not the user has changed the password. SRP6A doesn't have this issue. There's one theoretic advantage promoted in favor of OPEC, and this is also one of the main reasons why OPEC was selected by IETF. This is so-called pre-computation security. There's a formal definition of this notion in the OPEC paper. What this means is that when the server is compromised, so the password verifier is token, then the attacker will be able to do a brute force attack to find the password. This is possible for both OPEC and SRP6A. The difference between the two is that for OPEC, the attacker cannot use a pre-computed table. But for SRP6A, it's possible for attacker to use a pre-computed table, but attacker has to use a unique table for each user. So this requires a large amount of pre-computation and also a large amount of memory storage. So if you look at these two, we should see that the practical difference between the two is actually small. As a trade-off for pre-computation security, there are a few issues with OPEC. The first one is it relies on this mapping F function, and it's non-trivial to implement this F function. We already know that since 1996. And the second, it also relies on a key exchange function. In the original paper proposes to use HMQV, but after OPEC was selected by IETF, the authors modified the protocol to use a different key exchange function. The third, OPEC leaks information about password update to passive attackers, as I explained in the earlier slide. The main issue here is that the OPIC specification was incomplete in the original 2018 paper, and when it was selected by IETF in 2020, the specification was still incomplete. And the task to complete the specification was defined as follow-up work after 2020. But so far, this is still ongoing in IETF and not finished yet. So the takeaway from this IETF standardization process is that when this standardization finished in 2020, we should see that the augmented PIC problem was still unsolved. So that is motivation for us to look into this problem and try to find a different solution. That comes to part 3. And we are going to present a new protocol. But first, together with Van Oorschot, we did a systemization of knowledge in this field. So that covers about the past 30 years of research. We categorized PIC protocols into 5 classes. The first class is based on ideal cipher. Examples are EKE and all different variants of EKE. The second class is based on hash-to-group. So that is a F function used in SPIC, and all other protocols use the same F function as in the SPIC protocol. The third class is based on trusted setup. So this is the same setup as used in the dual easy random number generator. The assumption is that there's a trusted third party to define certain group parameters. But then the difficulty is to find such a trusted third party, and that there is a concern on the potential trapdoor. The fourth class is based on zero-knowledge proof, and JPEG so far is only protocol in this class. The next class is basically based on the design of SRP, and all other protocols are modifications of SRP in various ways. If we highlight the augmented PIC schemes in all these classes, we can see an apparent gap. The gap is that there's no augmented schemes in class 4. So back in 2008, the main idea of designing JPEG is based on the understanding that zero-knowledge proof is important. So far, this has been well accepted by the community. However, if zero-knowledge proof is important for balanced PIC, why no one has done it for augmented PIC? It turns out that we can do it for augmented PIC as well. So this leads to a new protocol. The main idea in this new protocol is still to use zero-knowledge proof to enforce players to follow the specification honestly, that follows the same design principle as in JPEG. Because the security of JPEG is well established, so the strategy here is to make minimum change to JPEG. But still, this results a new protocol called OWL. We name the protocol OWL because owl is one of the few animals in nature that have asymmetric body shape. And in this case, the protocol is asymmetric. Here's an overview of the protocol. During the registration phase, we compute a hash of the username and password, and we obtain this T. Based on the T, we can obtain pi and this big T. Big T is G to the power T. So we save pi and T on the server together with a username. And at the server, we also generate a public key X3. This is the same public key as used in JPEG, but in JPEG, this key was ephemeral. Here, we fix it for each user. The next phase is login. So the user sent 2 public keys and together with zero-knowledge proof to the server. This is exactly the same as in JPEG. The second flow, the server sent some public keys and zero-knowledge proof back to the user. And this is also the same as in JPEG, except that here X3 is a fixed key rather than an ephemeral key. In the third pass, client send alpha and zeroth proof for alpha. This is the same as in JPEG. But in addition, the client also send this R value. This R value is modulus Q. In other words, if we want to have 128-bit security, then the size of this R is 256-bit. So that is about 32 bytes. So with the extra 32 bytes, we convert JPEG from a balanced peg to an augmented peg. How is this protocol different from JPEG? In JPEG, we use 2 ephemeral public keys from each user. In OWL, this is the same for the client, but for the server uses only 1 ephemeral key, and the other key is fixed, so that is stored on the server. Because of this change, we require this multiple decision difficult assumption instead of DDH, but we prove that the 2 assumptions are equivalent. So in other words, the security of the modified JPEG is not affected. As a trade-off of this modification, we require persistent storage at one side. This is not possible in the balanced peg, but in the augmented peg, this is given because we have the storage at the server. Next, we look at comparison. So this is another view to look at the classification of different peg designs. So far, SRP6A is the only scheme that has been widely used. And you can see why. So SRP doesn't require any ideal cipher, doesn't require trusted setup, and also doesn't require hashed group. Despite the various limitations with SRP6A, at least the protocol is fully defined. So anyone who look at the protocol can implement it. This contributes to the wide implementation and use of this protocol. For completeness, we also compare with OPAC because it was selected by IETF as a new standard. After OPAC was selected as a standard in 2020, the protocol was modified in various ways. But however, the modification is not finalized. So here, I'm going to focus comparison based on the 2018 paper. First, we look at the round efficiency. In the registration phase, OWL only requires 1 pass, while 2 other protocols require 3 passes. In the login phase, all 3 protocols have the same number of passes. I want to highlight that in the original OPAC paper in 2018, the paper described the protocol as 2 pass for the login, but that is not correct because that will expose the protocol to an undetectable online dictionary attack. The latest version of OPAC paper has been updated, and the updated version requires 3 pass. So in terms of round efficiency for the login, this is the same for all 3 protocols. Next, we look at computational efficiency. Here, we look at 2 settings. One is in the mod-P group, so that is multiplicative group, and the other one is elliptic curve. For the mod-P setting, we further divide into 2 cases. One is using set prime as the modulus, another one is a DSA group. We do this separation because the definition of the F function critically depends on this group setting. In the mod-P setting, in the fully defined mod-P setting, as you can see that OPAC actually requires more computation than SRP. This is because here we use the same mapping functions, F function as defined in SPIC, and that uses a set prime as modulus. And in this case, OPAC is even more expensive than SRP6A. Under this mod-P group, OWL is the most efficient because of its use of the DSA, flexible support for DSA group, so the exponent is actually short. In the elliptic curve setting, we know the precise cost for OWL However, we cannot say the same thing for opaque, because the protocol relies on the definition of f function for the elliptic curve, and that is still an open question. Next is the message sizes. Again, we only look at the size in the fully defined setting. And in the fully defined setting, as you can see, that OWL actually requires the least amount of data because of its flexible support in the elliptic curve setting. OWL has flexible support for elliptic curve. This is because OWL only requires two operations on elliptic curve. One is addition, another one is multiplication. And OWL also requires a standard hash functions, so nothing else. Finally, we compare OWL with JPEG. JPEG is balanced peg. OWL is augmented peg, so the two are different types, but OWL is adapted from JPEG. In terms of round efficiency, the two protocols are the same. In terms of computation, as you can see, OWL is even more efficient than JPEG. That could be interesting to many people. If you look at the literature on this field, for the past 30 years, if you convert a balanced peg to an augmented peg, the conversion always adds more cost to the original protocol. But here, we don't add any cost. Instead, it actually saves cost. So why OWL can save cost? This could be explained by an open question we posed in 2010. So in JPEG, the protocol works by juggling 4 public keys in a symmetric setting. The open question we posed in 2010 is that whether 4 is a minimum number. And in that paper, we said we do not have a proof of minimality, so we leave this question open. In the symmetric setting, the next number after 4 is 2. So after JPEG was published, people tried to modify the design by using only 2 keys, but so far as I know, the modification, long of the modifications worked. However, here we are not talking about the symmetric setting, it's asymmetric setting. It turns out that in the asymmetric setting, we only need 3 balls. So that saves cost. And that is the intuition why in OWL we do more operations than JPEG, but actually the computation cost is even lower. As a trade-off for this, we need persistent storage at the server. So, but in the augmented peg setting, persistent storage at the server is given, so that is not any problem. With that, that is the end of my talk. I thank you for your attention.